Yeah,
everyone.
totally.
Several people asked if this could be recorded. So please, Sasha, tell us. Sasha's from the University of Chicago, as many of you know, and going to talk about her most recent paper with us.
Yeah, thank you all so much for coming, and thank you so much, Mike, for inviting me. I'm really excited to see that people are interested in our paper that just came out in PNAS. I'm going to attempt to pull up my screen and hope that Zoom allows it to happen.
Yes.
All right.
Looks good.
Okay, wonderful. And everyone can still see that when it's in full screen mode?
Yeah, perfect. Looks perfect.
All right, great. Well, yeah, again, thank you so much for inviting me, Mike. I'm super excited to talk to you all today about the narrow range of early habitable Venus scenarios that are permitted by modeling of oxygen loss and radiogenic argon degassing. Just super exciting project that just came out in PNAS. I'm back on March 6th, I think. Yeah, I'm basically just going to sort of talk through the paper in sort of more of a narrative way, hopefully with lots of fun pictures to look at. Yeah, let's go. So this is probably preaching to the choir a little bit, but why do we care about Venus is a good place to start when thinking about a project like this. And essentially, Venus is a wonderful kind of test bed within our solar system of what happens to planets closer to their stars, and particularly planets that are nominally Earth-like in terms of their size and potentially also their composition. And so hopefully looking forward to so many exoplanet discoveries coming out, we can think about what that means for our understanding of the habitable zone beyond our own solar system. So I just love this artist's impression of an exovenus, and sort of contextualizing Venus with what the habitable zone as we understand it looks like. Venus is kind of on that outer edge. So we're sort of really interested in understanding what is in that space in between Earth and Venus, not only sort of as they might exist today, but also as stars evolve over time, like our own sun and also other stars in the Milky Way, for example. So understanding this kind of gap between Earth and Venus and how these two planets that are in some ways so similar became so different. And there is reason to believe that there are plenty of exovenuses out there for us to look at in the coming years and also already. So understanding what we're actually looking at when we're seeing these planets that maybe look a bit more like Venus, and what that might be able to tell us about, we're seeing something that might not be habitable today. Does that mean this planet was never habitable? Or does it sort of reflect a different evolutionary process? And so that's kind of the motivation behind this study. And also, of course, we're interested in Venus because we're going back. So there are Veritas is, I understand, going through a little bit of a rocky patch right now, but with Da Vinci Plus and Envision coming up in the next decade or so, now is a really good time to be asking questions about what do we think we might be looking for when we get back to Venus with these upcoming missions. And so the sort of key question that sort of motivates this all is, could Venus ever have achieved habitable conditions? Currently, the surface is far too hot and the atmosphere is very dry. So it doesn't have the kind of classic ingredients for life and habitability, which is essentially, in this talk, I'll be referring to habitable conditions as surface temperatures at or above 273 Kelvin and presence of liquid water. And so could Venus have ever achieved habitable conditions? It looks like yes, based on a lot of previous work, including plenty of amazing work by people actually here in this call, which is awesome. So based on looking at Venus's accretionary history and simulations of that, like N-body simulations, the planet could have received up to 5 Earth oceans of water. So the ingredients were there for liquid water on its surface. And then modeling studies like those by McWay and other authors suggest that you could maintain habitable conditions through a thick reflective cloud deck for as long as most of Venus's history, up to as recently as 0.7 billion years ago. And there's also some work modeling starting from a magma ocean period on Venus, where the planet is able to evolve to condense water on the surface. So lots of signs point to, yes, Venus could have gotten to a state where it's habitable. But the question I sort of want to try and answer with this work, and sort of another way of thinking about habitability on Venus, is then how difficult it is for Venus to get to the planet it actually is today from one of these sort of hypothetical habitable scenarios. So essentially losing all of that water and kind of matching the atmospheric composition that we see today. And sort of how likely is this in the context of Venus's evolution? And so one way that we might look at the fate of Venus after a habitable era is considering the deuterium to hydrogen ratio in the atmosphere, which is kind of a proxy for water loss over time. Venus's deuterium to hydrogen ratio is about 150 times that of Earth, which could suggest as much as 3,000 meters of water lost from the planet over its history. However, this can be kind of a complicated proxy to unwrap. So it could be that you lost 3,000 meters global equivalent layer of water that was present as an Earth ocean of water sort of on the surface, or that water could be delivered and lost in kind of a steady state situation from degassing from the planet's interior, or impact delivery of water and then also loss of that water to space. And there are other complications as well, in that Venus's deuterium to hydrogen ratio might not necessarily have been the same as the Earth's. So it might not be quite so straightforward to interpret that 150 times number as a straightforward loss of more water. And there's also potential for the deuterium hydrogen ratio to be modified by different processes active on Venus during, for example, an early magma ocean period or something like that. So it's a little bit of a complicated number to unwrap, just because there are so many processes at play, and the sort of variety of mechanisms could operate from the very formation of Venus all the way through to present day, essentially. And so we have, fortunately, other constraints despite our relatively limited amount of data on Venus. And that is that we have this very thick, dry, oxygen poor atmosphere on Venus right now. So if you have water in abundance on Venus, Venus would eventually, in the process of getting to the surface temperature that it has today, evaporate that water, and then it can break up into hydrogen and oxygen in the atmosphere, and preferentially lose that hydrogen through escape processes. It's easier to lose than oxygen, and therefore lead to an accumulation of oxygen in the atmosphere. And some models for sort of exoplanets, I think, as well, by Tian 2015, kind of demonstrate that we might expect to see these oxygen-rich atmospheres on planets that used to have lots of water. So the fact that we don't have very much of this oxygen on Venus right now, I think it's about 50 to 100 ppm, it's suggestive that we need to get rid of that oxygen somehow if Venus ever had an enormous amount of water on the surface, as well as also losing that water itself, but that's generally easier to do. So what I'm going to do now is kind of go step by step through the model that we built to consider the fate of oxygen after a habitable era on Venus. So the sort of starting conditions for the model in the paper are that you have some early habitable climate with, you know, kind of arbitrary conditions really, but the main thing we care about here is how much water was there on this early habitable Venus and how much carbon dioxide was already there. And so we assume at the beginning of the model that all of the surface water inventory, anywhere between 10 and 1,000 meters global equivalent layer, enters the atmosphere as water vapor, and then CO2 starts degassing to achieve the modern atmospheric pressure by the time the model ends, of 93 bar or so. And then we sort of track the various loss processes and formation of oxygen by the loss of hydrogen from the water, and then also look at the various oxygen loss mechanisms that are in play in the model. So the first one is loss to space and sort of atmospheric processes of loss to space. So of course the loss of hydrogen, but also the loss of oxygen to space as well after this photodissociation process. And so for looking at hydrogen, we think about XUV and diffusion limited escape out from the atmosphere, depending on the atmospheric thickness and also the insolation received from the sun. And when the escape is really, really fast, we also include the dragging of oxygen out of the atmosphere as well, although in practice this doesn't happen a lot in our models. The more complicated loss process to sort of incorporate here is the non-thermal escape of oxygen to space. So in this model, we use the upper limit calculated by Gilman et al. 2020, and we also assume that the escape of CO2 over time is negligible. So this sort of oxygen loss mechanism is kind of fixed by those Gilman et al. Results here, sort of basically by this black curve shown in the figure here. And then the next major sort of pair of oxygen loss processes are related to volcanism over time as the atmosphere is degassing on Venus. So the total number of carbon species degassed essentially adds up to the total sort of number of carbon atoms present in Venus's present day atmosphere. And so as this volcanism proceeds, you gain two oxygen loss mechanisms. The first of those is reducing atmospheric species like carbon monoxide and methane, which can be oxidized to CO2 and sort of consume oxygen in that process. And then also the oxidation of volcanic products on the surface. So in this case, we assume basaltic volcanism with composition similar to mid-ocean ridge basalt on Earth. And in this oxidation step here, we also include the option for oxidation of explosive volcanic products. So if explosive volcanism occurs in the model, we assume that 100% of those products are oxidized, but otherwise we assume just 10% based on the diffusion length scale of oxygen in solid basalt. And so to set the outgassing and therefore volcanism rate on Venus throughout our model, we assume a variety of different concentrations of carbon dioxide in the melt that's reaching the surface. And we set these sort of comparable to terrestrial mid-ocean ridge basalts, but sort of on the upper end of those concentrations. We assume a very simple model for the outgassing rate over time, just exponential decay, basically, of crustal production rate. So it matches present day estimates by the end of the model and is at its maximum right after the end of the habitable era. And then at each time step, given the melt water and carbon dioxide concentrations, we calculate the degassed species, carbon and hydrogen species at each time step, and then use that to kind of evolve the atmospheric pressure over time. And we also consider melt oxygen fugacity as well in this speciation calculation. And then the final oxygen sink that we consider is oxidation of a molten surface. And this is kind of like an on-off switch mechanism in our model, where we sort of separate our results into a case where we don't have a runaway greenhouse at the end of the habitable era, and then this case where we do. And during that runaway greenhouse, we consider the option that the surface temperature might be so high that you're actually able to melt the surface of Venus and basically speed up the diffusion of oxygen into the melt and remove oxygen that way by oxidizing a molten basalt layer at the surface. And so to do this, we calculate the surface temperature at each time step during this runaway greenhouse era as a function of the atmospheric water abundance. We're also including dissolution of the water into the melt and exsolution back out again as that melt solidifies. So it's kind of a interesting balance there. And then using that surface temperature, we calculate a temperature profile in the subsurface just using diffusion. And then we use alpha melts to calculate how extensive the surface melt layer is and assume that any melt present can be oxidized by oxygen present in the atmosphere to kind of maximize the size of this oxygen sink. And then, so here's a little table that sort of summarizes the 7 different model parameters that we consider here, leading to a total of about 47,000 model runs. So we equally weight each of these different parameters for each different value within these parameter ranges here. And yeah, just to give you sort of an idea of the parameter space that we're working in. And so the sort of ultimate takeaway from this sort of model overview is that oxygen sources need to, during Venus's post-habitable era evolution, need to at least match oxygen sinks and also often be smaller than those oxygen sinks, so we can actually get to the low oxygen concentrations in Venus's atmosphere today. And I'll give you a quick little spoiler here that this is pretty tricky to do, and then move into sharing with you some of the results to kind of prove that it is in fact as difficult as I'm saying it is. So here's an example series of model runs for a case where we start with 100 meters global equivalent layer of water on the habitable Venus, and also have melt concentrations of 500 ppm CO2 and 0.001 weight percent water, so pretty dry. And in this case, we're assuming that all of the melt is reaching the surface as extrusive volcanism, so like lava flows, and that the majority of Venus's atmosphere is coming from volcanism and degassing of CO2 after the end of the habitable era. And so you can see that all of these different purple curves are and blue curves in the case of the oxygen are individual model runs, and basically, and for a model run to succeed, it needs to finish underneath these dotted lines that say modern Venus water and modern Venus O2, and those are the concentrations in the atmosphere. And the overwhelming majority of these models actually fail. in that you are not able to lose enough oxygen basically over time to match the modern Venus oxygen. The water is a little less challenging to do just because the hydrogen escapes fairly readily from the top of the atmosphere in our models. But in addition to this oxygen loss constraint, we can actually consider another constraint, and that is argon-40, which is not super abundant in Venus's modern atmosphere and kind of places a constraint, although I will sort of preface this by saying it's a relatively loose constraint on the degassing of reduced species and overall eruption of crust on Venus since the end of this habitable era. And so here's a little sketch of the sort of argon degassing model here, sort of illustrating that you have the potassium-40 in the mantle decaying to argon-40 over time, which are both preferentially partitioned into melts. And then as that melt is erupted onto the surface, you can either degas argon-40 directly from that melt, or as the potassium-40 in the crust now decays over time, that is also released to the atmosphere and kind of evolves. But we're also including sort of burial of that crust, so the potassium-40 can also be returned to the mantle. And so based on Cowler 1999 and O'Rourke and Coronaga 2015, we run a series of argon-40 degassing models for a variety of parameter combinations. So here are just some example cases. So for each of these melt production rates in the top panel here, those match melt production rates that occur in our oxygen loss model. So we can kind of translate the argon results across basically. And then on the lower panel is showing the evolution of atmospheric argon-40 in kilograms. And the dashed line here is the present day argon-40. So we're trying to sort of get below that line basically. So you can see the kind of yellowish and greenish curves are successes in this case, whereas the bluer and more purple curves are failures by this sort of argon-40 metric. And so there are a fair number of unknowns given that this process refers to or is connected to properties of Venus's mantle. So we look at a fairly wide range of different parameters here, including crustal thicknesses, which basically affect how much of that potassium-40 that makes it to the surface is actually reincorporated into the mantle rather than degassing argon-40. And we also consider different mantle melt fractions and different primordial mantle compositions as well to kind of get a range of results for this. And we equally weight each of these success percentages basically for each of the different parameters we consider for the argon model, and then basically match these across to the oxygen loss model parameters as kind of a mean argon success rate for each given oxygen model result, and then sort of multiply through. And so when we combine the results of the oxygen loss model and also the argon model, we can look at the sort of overall results from each of these 7 different parameters and sort of how they interact with each other in a plot like this, which is definitely something I encourage you to go have a closer look at in the paper as well. But it sort of highlights here in these sort of yellow and green colors the optimal regions of parameter space for reconciling a habitable Venus with the Venus we see today. And so I'm going to sort of dig through these results in a little bit more detail. So ultimately, what this plot tells us is how you can get from a hypothetical habitable era on Venus to the planet we see today. And you have a variety of options. And the first is ending habitable conditions early. So what you can see in the left plot here is 2 cases with exactly the same parameters, except for the timing of the end of the habitable era. So the solid lines ended 4 billion years ago, and the dashed lines 3 billion years ago. And what we can see is that earlier on in Venus's history, there's a slightly greater non-thermal loss of oxygen to space, which is enough to basically kick you into a regime where the oxygen sinks, balance or overbalance the oxygen sources. Whereas if you start that model a little bit later, you actually end up with too much oxygen left over in the atmosphere. And so we can see even more clearly sort of the summary here in the bar chart of the difference in the percent of successful runs as you step from a habitable era ending 4 billion years ago to one ending 3 billion years ago. There's sort of a factor of a few there. So yeah, just to recap sort of reasons for this, the younger sun drives faster hydrogen escape, which means you have more oxygen in the atmosphere to lose by the more active oxygen loss processes like the non-thermal loss of oxygen, and also the oxidation of lava flows or degassed reduced species as well. But it's also important for the argon constraint because it gives you less time for the potassium 40 to decay in the mantle before that potassium and that argon are basically brought to the surface and that argon can enter the atmosphere. And the other constraint here is that you need to end with less than 500 meters global equivalent layer of water. So the largest water inventory in these cases that works in our model is about 300 meters, with a caveat that I'll get to later. But essentially, as you drive to higher and higher habitable era water inventories, it's more and more difficult to lose all of the oxygen by balancing it with oxygen sinks. And when the 40 argon constraint is added as well, this falls to 300 meters. But we can kind of get around this maximum water at the end of the habitable era in a couple of different ways. And the first of these is to erupt melts with very reduced melt oxygen fugacities. And this basically increases the size of the oxygen sink to oxidizing carbon monoxide and methane. And so you can kind of see how that works for different oxygen fugacities here on the left-hand side, and also summarized in the bar charts. And if you don't do this, the problem is, if you do appeal to this mechanism though, something that's really important is that you actually need to add oxygen over the course of the model evolution, or you can end up in a scenario where your atmosphere has far too much carbon monoxide or methane in it. And so you can kind of see this illustrated on the right-hand side here, where we've got this dark purple on the left-hand side with these lower or these drier melts, whereas you need wetter melts at these lower oxygen fugacities to account for how much carbon monoxide and methane you're degassing. Yeah, so just sort of summarizing that again here, you can end up pretty easily in these models with a atmosphere that's got far too much carbon monoxide in it relative to the measurements we actually have of Venus's atmosphere. And another conclusion that we kind of came to within the framework of the model in the paper is that actually the runaway greenhouse melting sink for oxygen, so this molten layer at the surface of Venus, is not that important for actually affecting our results. So it adds a little bit of additional habitable era water in a couple of cases, but overall it's a much smaller effect than some of the other oxygen sinks that we're looking at here. However, the model results that I've just shared with you here actually only constrain the surface water inventory at the end of the habitable era. So you need to end with less than 300 meters global equivalent layer of water in the sort of more oxidizing mantle cases. But something else we wanted to include in this paper is what does that actually say about the average water inventory during the habitable era itself? For example, if you're able to actually have a net transport of water into the mantle over the course of that habitable era, sort of by some subduction adjacent or analogous process. So the model we consider to sort of take into account this effect is a kind of vertical conveyor belt style, very simplified model that's sort of analogous to a sort of heat pipe or very simplified stagnant lid tectonic regime for Venus. So during the habitable era, you're able to form hydrated crust, which is buried over time by later volcanism and kind of pushes the earlier layers of crust downwards into the mantle. And then what we do to determine whether or not that water goes into the mantle in the hydrated crust or if it re-enters the atmosphere is basically look at different pressure, temperature evolutions for different thicknesses of crust and see in which cases you have serpentinite dehydration occurring first, which would release water back into the atmosphere, versus eclogite formation, which would make the basalt transform into more dense eclogite that can then sink into the mantle. And so by looking at a variety of different hydrated mass fractions for that hydrated crust forming during the habitable era and different volcanism rates, we sort of get a bunch of curves like these that show how the water inventory can actually evolve over the course of a habitable era. Or so in this case, the habitable era ends 4 billion years ago, but we look at these sort of 0.4 billion years beforehand, and you can actually get the habitable era to sort of lose water to their mantle over time. And so to kind of consider what these different amounts of water might look like, I've made these sort of fun plots of different amounts of water sort of visualized on Venus's present topography. And you can easily go from cases with about like 1,000 meters global equivalent layer on the surface to 100 meters global equivalent layer on the surface during a habitable era with this relatively sort of simple idea of water recycling. And so we did this a bunch of different times for a wide variety of different parameter combinations to make a summary plot like this and think about the mean habitable era water inventory. So we found that for certain cases, you could actually find habitable era scenarios where you end with the right amount of water to match our oxygen loss models, but you actually have a much higher mean habitable era water inventory. So looking at A prime, B prime, and C prime here. So you could have that 100 meters at the end of a habitable era, but actually the average over that 0.4 billion years or 1.5 billion years might be closer to 1,000 or 500 meters of water, which is a much more sort of generous habitable case. But that still comes with the caveat that you need to go through a relatively narrow range of parameter space to then evolve to modern Venus, even for pretty dry end habitable era scenarios. And so how does this series of model results, both from the oxygen and argon-40 modeling and the potential recycling of water, fit into what we might look for on Venus with upcoming missions? And so important measurements to take into account is d/h. Again, although I said at the very beginning that this might be kind of a more difficult number to unravel, any improved constraints on this and how water is lost from Venus over time is going to be important in understanding the planet's overall evolution. And also what these missions will hopefully provide us with is a better understanding of the planetary system kind of as a whole. So high resolution topography and gravity data would be great for any kind of constraint really on Venus's tectonic regime. Lithospheric thicknesses would be super important for sort of comparing with some of the numbers that we've used in the models that I've described already, but also anything that can constrain how wet melts might have been on Venus over time will be really important. So potentially distinguishing between the sort of two success cases I described, where either you have a more oxidizing or melt oxidation state and pretty dry melts and smaller amounts of water, or you're in a regime where you have much more reducing melt oxygen fugacities, but also wetter melts erupting over time. And so any constraint on sort of magmatic processes on Venus will be really important for sort of feeding back into the model results that I've been talking about. So just to kind of wrap up and go over conclusions, it is possible to reconcile an early habitable era with Venus's 1 atmospheric composition. You can go through that evolutionary process, and that requires oxygen sources to balance oxygen sinks. However, this balance is only achieved in a very small percentage of our model runs, less than 0.4%, and only under very specific conditions. And this is referring to the oxygen loss models and the argon-40 eruption models. And those conditions are that the habitable era must end before 3 billion years ago, kind of regardless of everything else. Secondly, the water inventory at the end of the habitable era must be less than or equal to 300 meters global equivalent layer, unless you have melt oxygen fugacities less than FMQ -3. And then in that case, you also need water to be added to the system. And yeah, average melts erupted on Venus after the habitable era must have had greater than 0.28% dissolved water, unless Venus melts have had high oxygen fugacities. So those two and three kind of go hand in hand there. And then finally, if there was net transport of water into the mantle during a habitable era, you could have had a mean habitable era water inventory that was higher than these end habitable era constraints that I've been talking about. However, you're still subject to the very small fraction of model runs that are able to replicate modern Venus's atmosphere within the framework of our model. So that kind of wraps up the slides that I have prepared. I'm really excited to chat with you all during the discussion. And yeah, thank you very much for coming along and taking the time to listen.
Great. Thank you so much, Sasha. That was excellent presentation. Okay, if people have questions, they could raise their hand and then I can call on you if anybody has questions. Maybe it was so clear there'll be no questions. I can ask a quick starter question. So you talked about the FMQ being, if it was way out of like very non-more, basically, right? -3 or -4. But then you were also saying that you have this issue with reduced species ending up in the atmosphere, and those have to be oxidized. So I'm wondering how that comes about. Are you saying that these reduced species are also outgassed at the same time? Is that what happens? And what is the basis behind that? Is that going back to like Gaillard's models and people like that, and understanding what reduced species come out of in such an FMQ -3 scenario?
Yeah, exactly. So we use Wogan et al., I think 2020's bulk gases model to actually calculate the speciation. So the only kind of constraint that we're placing on the amount of hydrogen and carbon species coming out of any degas melts is that you need to achieve the amount of carbon dioxide that Venus has in its modern atmosphere. So sort of saying, if you have this amount of CO2 dissolved, how does that speciate depending on the oxidation state of the melt? And so those Wogan et al. Models match the Gaillard and Scaillet calculations for how speciation varies with the oxygen fugacity, temperature, pressure, and the concentrations of water and CO2.
Okay, great. Thank you for that. That was really nice explanation. Anybody else have questions? Go ahead, Kathleen.
Hi, Sasha. Really cool talk. I was wondering if you could maybe just explain a little bit more about what you mean by the end of the habitable era being like a parameter. Does that not have to be like consistent with like luminosity, amount of water present at start and CO2, or it's just, I guess I'm having a little trouble.
The sort of setup that we considered here was to try and be kind of agnostic to whether like the processes that lead to actually having a habitable era, what happens if you assume that Venus does become habitable, and then kind of see what happens afterwards. So in this case, we sort of picked a range of 3 different habitable eras ending points. So 4 billion years ago, 3 billion years ago, and 1.5 billion years ago, just to kind of see how that endpoint affects our model results. So the sort of assumption there is that prior to that endpoint, a process like, volcanism leads to a greater greenhouse effect, and that kicks you into a runaway greenhouse, for example, or you go into a sort of moist greenhouse where you're hemorrhaging water to space to end the actual period of habitability. But what we're looking at is just kind of what comes after that. And obviously in Venus's real case, it's not tied to a specific like end date, right? But seeing the results for those 3 different endpoints kind of gives an impression of how likely you would be to get from a habitable Venus to present day Venus, depending when that habitability ended. Does that make sense?
Yeah, I guess maybe I can rephrase my question. So like if the habitability period ends and you have a certain amount of, you have that parameter, and you have a parameter for like amount of CO2 and amount of water at that point, what happens if like your temperature profile would say like some of that water should be condensed on the surface? Does that make sense?
Okay, yeah, I see. So we're assuming at the beginning of the model that we've sort of gone past the point of no return for recondensing. So typically in our models, we degas a huge amount of CO2 relatively quickly. And so we don't actually explicitly calculate the surface temperature in the post-habitable era section, but we sort of assume that Venus is now beyond the point of no return.
Is that okay, Caitlin? Does that answer your question?
No, I'm still a little confused, but I won't take up any more time.
No, it's okay. So if you can rephrase, if you can think of something else, please bring it up. Let's see. I was going to also mention something I thought was kind of interesting in the paper. You talked about this possibility for higher surface temperatures and the surface becoming molten and being very efficient, of course, depending on the FMQ buffer again, at pulling down oxygen. I've always thought this is kind of interesting, that there has been this idea around for a while that the surface temperature could have been, over 1,000 Kelvin and such things. And that would answer kind of some puzzle that we have today, right? I mean, most people think that Venus probably had a intrinsic magnetic field at some point. And, Joe O'Rourke wrote a paper a couple of years ago showing how the surface temperature is below the Curie point. So there should still be remnant crustal magnetism on Venus. We just haven't been able to detect it because we haven't gone low enough. Basically, we need a balloon mission. That's what Joe's arguing for. But if you had temperatures that were well over 1,000, then you're well over the Curie point. And that would be an explanation why we don't see any crustal remnant magnetism. So that could be an argument for it. I mean, since we don't have any good arguments for why Venus doesn't have a magnetic field today, that might be an argument for why it doesn't have crustal magnetism. That could be a constraint in the models, in a sense, saying it definitely was much hotter, maybe even in a molten stage. I don't know.
Yeah, no, that's a really good point.
Yeah, that was kind of cool. And then I was also a little confused about something probably on the paper. You're saying that it was like the fourth point in the limitation section. You say we assume Venus's eruptive history can be models in exponential decay, which you talked about here. But then later you say in the same paragraph, we offer continuous volcanism in our models because this maximized lava flow. So I'm a little bit confused. You have exponential decay and then you have continuous. So what are you doing?
I think maybe the word choice continuous there wasn't ideal. So when I say continuous there, I mean rather than sort of like one enormous pulse of volcanism, like in a resurfacing event, for example. So continuous is in there are no breaks in volcanism. So you go just through this exponential profile.
Okay, cool. Sorry. Yeah,
okay, my bad.
No, my bad reading. Okay. Sonny has his hand up. Go ahead, Sonny. With your question.
So Sasha, this is really fascinating. I'm sorry if I missed it earlier, but I was curious because you dwell a little bit on dragging off oxygen, but water isn't that much heavier, and I wasn't sure if you had thought at all about. And again, apologies if I missed it. If you had thought about how dragging off water might also affect your initial estimates and where you ultimately end up.
Yeah, that's a good point. So we don't model like dragging of water as a molecule. We assume that all of the water that reaches the upper atmosphere photodissociates, which is sort of a common assumption for other models like Wordsworth et al. I think 2013 do the same thing. So we just assume photodissociation to kind of maximize the amount of oxygen we're producing early on so that it can be subject to these lots of mechanisms. But losing the entire molecule is also an interesting thing to consider. Thanks.
Okay, there's also a question in the chat, unless Arnaud wants to unmute and ask himself. There he is.
Hi, everyone. Yeah. Hi, Sasha. Thanks for the great presentation. I really like this, the paper and your presentation. So I was wondering, there's also some alternative scenarios now that propose that there could be non-efficient magma ocean outgassing. So I was wondering how this could affect your results and how this could reconcile with some of your potentially habitable scenarios.
Yeah, so if you have sort of non-efficient magma ocean outgassing, I guess my sort of first thought there is that you're maybe more likely to have really high volatile concentrations, particularly sort of early on, and even maybe continually over Venus's history. So depending on how that would affect kind of how much CO2, how much water you're able to outgas later on, could sort of change which of these regimes is more likely, right? So if you have this very wet Venus mantle, for example, you would probably want to be in a case where you are degassing more of these reduced species, carbon monoxide, methane, so that you don't end up with too much oxygen just from volcanism, not even from a habitable era on Venus, necessarily with like a condensed water layer. Yeah, so in terms of other species, I guess I'm not 100% sure how that would work with the inefficient magma ocean outgassing. But yeah, depending on sort of where Venus started is sort of a pretty important constraint on how do you get to habitability in the first place, right?
Yeah, for sure. Yeah. Thank you.
Yeah.
Okay, maybe I can ask another quick question. So maybe I got lost a little bit, but you were talking about this Gilman paper and his escape models, basically. But one thing in Cedric's work is that he assumes the planet always has the same CO2 dominated atmosphere, basically. And that's probably not a really good assumption, especially if you consider the habitable period. So how did that play into your calculations? Or were you just using it as kind of a baseline, or what was going on there?
Yeah, so we're using that as a baseline, and then depending on whether or not there's actually oxygen present in the atmosphere, we sort of use that as an upper limit on the oxygen loss. But that is one of the points that I think is going to need a lot more work in the future, is sort of how do you have these different oxygen loss, non-thermal oxygen loss rates changing with like arbitrary atmospheric composition. And that's not something we were able to do for this, but would hopefully be something that going forward in the future will add into sort of our understanding of how Venus might have evolved, if you had much more water or much more oxygen in this at any point in Venus's history, and what that means for oxygen escape. But my understanding is that that's still a pretty hazy space in terms of our understanding.
Yeah, I think there's some truth in that. I was gonna say another thing that's interesting is that, of course, we don't have any constraints on Venus's obliquity in its earlier history, of course. And there has been a really interesting paper by Shuangfei Dong, who was showing that if you orient your magnetic field lines directly at the sun, it's very easy to get lots of outflow at the poles, tremendous amounts. I'm not sure if anybody's done it for a solar type star. I think he was doing this for an M dwarf, but it could be other scenarios where, not only composition, but even the orientation of your magnetic field lines, assuming the planet, where you could get huge amounts of outflow. So I think you're right. This parameter space is scarily large, not to mention, like you were saying about the argon 40, the potassium to uranium ratio, which we don't have good constraints on. I mean, there's still a lot left there. And also this, like, understanding the oxidation of the surface, where is it sitting in a sense? And that's going to be very hard to get from any of the missions, unfortunately, that we have on the table right now.
Yeah, definitely. Yeah, I love that we sort of assume that magnetic fields are like helpful for protecting an atmosphere, but like you're saying, there are so many models where it's just like, this is a great way to just throw your entire atmosphere into space. So more work on that stuff would be really cool to see.
Yeah, I mean, composition plays a big role too, right? If you look at like in the paper with Colby that you cited, where you showed this plot, in there we actually show some models from Manuel Schwerf and Helmut Lammer and Moa Persson showing escape rates from Mars being much higher, and much lower than Earth and for Venus, right? Depending on what the phase of the sun is and stuff. So composition is key as well. So, okay. Any other questions from anybody? I don't want to keep people any longer than they want to be here. No? Okay, well, thank you so much again, Sasha. It was really excellent. We really appreciate you coming. It was fantastic. And give Edwin our best.
Will do.
And good luck in your future. And again, great talk. Okay.
Thank you so much.
Thank you all for coming.
Thank you.
Thanks a lot. Excellent.
See if I can end the recording.